Hello and welcome you all to the NPTEL course where we are discussing the electroweak interactions in the standard model of particle physics. And so far we have done well, and we have basically introduced one of the fascinating theories that ever have been discovered in the humankind, which is to talk about the quantum electrodynamics, and where we could actually make the photons interact to electron using a gauge theory principle, E1 gauge theory, so to say. And then on top of that, we actually did one thing which is to kind of calculate the propagators for the fermions and also for the vector bosons, which are the photons, so to say, within the paradigm of QED. And today we are going to actually derive or rather we are going to focus on what we call the Feynman diagrams which actually govern the QED interactions. But before we do so, we have to introduce a cute concept which is called the S matrix. Let's do that first, and then we will come to the Feynman rules in QED. Okay, so let's talk about S matrix. Now you remember that we actually did the canonical quantization to some extent, not in great details of course, but to some extent we highlighted how exactly different fields can be expanded in terms of the operators and can utilize their impose either commutation or anti-commutation relations of those field operators to basically bring out the particle interpretation out of them. And that is how this field psi is now interpreted as electrons, or the field mu is now interpreted as photons, and so on and so forth. But remember that this canonical quantization essentially works for the free or the non-interacting particles. Now, whenever you bring in interactions the way that we actually did in QED, that essentially brings you perturbations. So, the interaction involves the creation and destruction of particles, and that basically gives you the scattering, and this is what is encapsulated in this terminology which is called the S matrix. Why S I do not really know. Perhaps it is to say that it is a simple matrix or something, I do not know. But it is a kind of time evolution operator. Now what kind? Suppose you have two particles colliding, one which I am drawing by this solid blob and the other by this transparent blob, which approaches from far and then they eventually collides at this place, and this is governed by this interaction Hamiltonian, otherwise this interaction will not happen, right. So whenever we talk about interaction, this interaction terms have to be there, and let us call that Hamiltonian the full Hamiltonian of the theory, which is like H, and then they recede, after the collision they recede. So this is basically the picture that you have. So in a sense you can say that total Hamiltonian has a free Hamiltonian where the canonical quantization applies, and then there is this interaction part which is this H prime. And in the Heisenberg picture, essentially we say that the state vectors do not change with time, but the operators actually does. So you can say that this state psi, which I can call P1, P2, the two particle state, if I am thinking at t equal to minus infinity, that is actually at the initial stage when the particles are very, very far. On the other hand, the final state is represented by Q2, Q1, which is also, so there is a tagline which I am adding, which is called the simple world. Now this simple world basically means that this is actually described by this free Hamiltonian or H naught, where the canonical quantization description essentially applies. So this is for t tending to infinity, which is actually far after the scattering. Otherwise, if you basically have to talk about the outcome when the scattering is taking place, we basically say the in state to be P1, P2 with this notation that we can say that this is the real world. I mean, this state has to be evaluated in the presence of that perturbing Hamiltonian H prime, which we have introduced, right. Similarly, the out state will be Q2, Q1, and that will be Q2, Q1 real world, not the simple world that we are talking about. So basically if we have to calculate the outcome of this scattering experiment, then basically we have to find A, which is nothing but the expectation value of Q1, Q2 out real world with P2, P1 in real world. Now, what we can say that we can rephrase this in terms of Q1, Q2 simple world with this S matrix sitting in between and P1, P2 simple world. So, S matrix is a matrix element of S operator which pertains to the specific in and out states. Okay. So, what we basically need, that we need this H0 to describe the simple world states, whereas the expression for S operator we actually require, and we can then use the eigenvalues and the eigenstates of H0 to find out this amplitude. So, basically in this way we have to find the expression of the S matrix. Now, I am not going to do this in details, but what I am going to indicate is that if you do this exercise in details, you will find this in any quantum field theory book, say for example, and then you will find that the expression for this S matrix. So, this is once again the simple world phi S psi simple world. This is what the amplitude that we are interested to calculate, and this can be expressed in terms of this is basically phi psi in the real world, okay, and they coincide at t equal to 0, and then you can find out that this expression for this u is essentially the time ordered product of e to the power minus I t1 to t2 dt HIT, where HI represents the interacting Hamiltonian. So, this is the key expression that we actually has. So, this is the expression of the S matrix, so to say, and or rather you can say that the S matrix is nothing but this ui when t2 goes to infinity and t1 goes to minus infinity. So, that basically means this is the time ordered of e to the power minus I integral of minus infinity to plus infinity dt of HIT, or you can say that this is HIX integral of d4x e to the power minus I from minus infinity to plus infinity. So, this is the expression of the S matrix that you actually have. Now, what you actually do, that you actually expand this S matrix in a Dyson series e to the power minus ix, that will have the first term like minus I in minus infinity to plus infinity d4z hiz, and then you have two terms like hiy and hiw integrated over d4y, d4w and so on. So, the S matrix is essentially the time ordered thing of this whole series, and this is what you call the Dyson series. Now, what we need to do, that in case of QED one needs to expand this. Now, I am not going to do that mathematics for you. What I am going to say, that this is going to represent a set of graphs. You can represent all this perturbative expansion in terms of some simple looking graphs, and from the Feynman rules we can impose some Feynman rules to those graphs, and from that we can simply calculate the outcome of different processes, and that is the beauty of using this Feynman rules technique. So, let us go and see what we can do for the Feynman rules in the QED. So, once again the process is a little detailed, and that will be perhaps appropriate for a quantum field theory course or a dedicated course on QED. But for us, what we need, that we need to find the Feynman rules for QED which we can utilize to compute different processes, and this essentially comes from the S matrix that we just talked about. Now, what are the possibilities that we actually have? In QED, what are the things that we have? We have a initial state particle, we can have an initial state antiparticle, we can have a final state particle, we can have a final state antiparticle. I mean, in terms of electron or proton, we can have an initial state photon, we can have a final state photon, we can have a photon mediator, we can have a fermion mediator, right. So, these are basically the ingredients of how to define the different interactions in the QED. Okay. So, let us first start with the initial state particle. Now, how to describe an initial state particle? The initial state particle will be essentially described by a particle which is essentially annihilating into the vertex. So, I will sort of redraw this thing. So, this dot, say for example, reproduce or represents the interaction vertex, and a particle is initial state particle, means it is coming and annihilating into the vertex. Now, an annihilating particle is represented by what kind of spinor? You all know that this will be by u of p. Now, remember that we have to somehow distinguish between the particle and antiparticle. So, for that what we do, that we draw a straight line like this, we put an arrow here like this, and there is another arrow that I explicitly put on top, this double arrow. This is what is called the momentum arrow, and the arrow which I am drawing on the line of this one is sometimes referred as a fermion arrow. And for a particle, this, you can also say that this is the direction of the spin or something, but whatever. So, fermion arrow and the momentum arrow, when they point or do point along the same direction, this basically represents a particle like state, and this is initial state particle or annihilating particle, because this particle is annihilating into the vertex. So, this is basically how we talk about, this is my rule to describe a initial state particle. The mathematical representation is UP, the pictorial description is exactly like this. Now, I have to talk about a final state particle, say for example. If I have to talk about a final state particle, then I have a vertex once again, and the particle is actually, final state particle means it is being created, right. So, this is actually outgoing from this particular vertex, and once again, just because this is a particle, the momentum arrow and the Feynman arrow will be in the same direction. And how do I represent that? A particle creation, this is something that I can do by writing u bar p, and this momentum, of course, that I am referring to this is p for both the particle and antiparticle that I am talking about. Now, let us talk about the initial state antiparticle. So, initial state antiparticle, you know that for antiparticle the definitions are all matlab it has a reverse notation, right. So, therefore, the initial state antiparticle is represented by V bar of p, and once again initial state antiparticles means the antiparticles which are annihilating into the vertex. So, if this is the vertex, then basically the momentum is actually flowing towards the vertex, and so the fermion flow or fermion line, this arrow will be flowing out of the vertex, and this clashing momentum arrow and the fermion arrow is basically denotes that this is not a particle but an antiparticle, and this is denoted by V bar of p. So, this is my initial state antiparticle. Now, let us talk about the final state antiparticle. The final state antiparticle means antiparticle which is created out of this vertex, and this will be governed by, once again you have the vertex, and the momentum will be flowing out of the vertex because you have created this antiparticle, and once again the spin flow should be actually pointing towards the vertex. That means it has to be opposite, so that we can distinguish between the fermion and antifermion. And once again, what will be the mathematical notation by which we can denote this? It will be simply V of p. So, this is the creation of antiparticle or final state antiparticle. Okay. So, now let us talk about the initial state photon. That means a photon which is getting annihilated. Once again, you remember the mode expansion. So, therefore, you can say that I can do it represented by epsilon mu p, whereas this momentum will be, momentum p is actually flowing towards this vertex. And you see the fermion lines are actually the solid lines, and the photon lines or the gauge boson lines, those are actually wavy lines like this kind of lines. Okay. So, this is how we So, what will happen to final state photon? Final state photon means a photon which has been created. So, once again, if this is the vertex, then the momentum is actually flowing out of the vertex, and this is once again momentum p, how do I mathematically represent this vertex, or rather this is photon which is being created? You can say that this will be described by epsilon mu star p, correct? So, this is how I can represent the photon which is being created out of the vertex. These are essentially the polarization vectors that we talked about. Now, we have the photon propagator. Now, this is precisely what we talked about. So, the photon is essentially propagating between two vertices, you know, and the Lorentz indices associated with the two vertices are mu and nu, and suppose the momentum is q. So, how do I write it? This is precisely what we discussed in the last lecture, and this is going to be minus I g mu nu by q square plus I epsilon, correct? So, this is what represents the photon which is propagating between two vertices, correct, okay. And then we also have the fermion propagator, and the fermion propagator is essentially, once again pictorially, instead of the wavy lines that I now have a solid line like this one, you know, with a fermion arrow, and just because this is a fermion, not an anti-fermion, so the momentum is along the direction of the flow. And so, therefore, what is the expression for the fermion propagator? Now, this is also something that we talked about. This is gamma mu q mu or q slash plus m by q square minus m square plus I epsilon. Very good. Now, the last thing that we have is essentially the QED vertex. Now, the QED vertex is something that we have already seen. So, this is represented by the term J mu mu, right? This is giving you the interaction between the electron and the photon. And what is the vertex factor that we usually assign? This is essentially minus of I q into gamma mu. So, this is how we actually define this interaction vertex. So, this is the interaction vertex from which there is a photon connection and there are fermion lines. So, this is what is defined as a QED vertex. So, this completes our list of possibilities which actually enters into the construction of different QED processes. So, once again, to remind you that the convention is that for the particle, the momentum arrow and the fermion arrows are in the same direction. For the antiparticles, this is in the opposite direction. Remember that the initial state particle is essentially annihilating particle, initial state antiparticle is annihilating antiparticle. Final state particle is particle which is created, final state antiparticle which is antiparticle created. Similarly, initial state photons and final state photons and the propagators of photons and fermions, and of course, the vertex factor, and this is once again the convention, so to say, which actually gives you the correct amplitude from the S matrix. So, that is what we talked about. So, these are the three parts which actually constitutes a Feynman diagram, which actually describes a process or gives you an amplitude for a particular process. One, the external particles, number two, the vertex factor, number three, the propagator that you actually have, and the product of these three will give you minus Im. Remember, this is what we actually talked about, which actually comes this matrix element squared that we calculate, which goes into the expressions of the cross sections and decay width, and that is essentially, so the product of 1, 2 and 3 is going to give you minus of Im. Before I conclude today or go into constructing one of the examples of the Feynman graphs which we are going to calculate next, let me give you an interpretation of the QED interaction vertex. Like, as we all remember now that the QED interaction vertex comes from this interaction term that came from this U1 gauge invariance of the Lagrangian, which is of the form like Q psi bar gamma mu psi mu, right? And we said that this essentially represents one vertex which is like this one in the picture, that you have a fermion line here, and then I just put two fermion arrows here like in this direction, and then this wavy line represents the photon, and we said that the vertex factor is nothing but minus IQ gamma mu. So, you see that this q is there, this factor of gamma mu is there, and of course, this psi bar and psi is essentially going to represented by those external lines depending on whether they are particle or antiparticle. So, that raises the question that what does this kind of a vertex essentially represents? Do you have initial state particle? Do you have final state particle? Do you have particle scattering, antiparticle scattering, particle annihilation, antiparticle annihilation? What does this Feynman graph, this interaction vertex represent? I will tell you now that this vertex essentially can represent many possibilities, actually 4 possibilities. The first one is actually the electron scattering. Suppose, so this all depends on how you are drawing the momentum arrow. So, suppose in this picture, if I put the momentum arrow, so this is the picture, this is how I identify the fermion line with this arrow, as I have pointed out, this is the vertex and this is the way the photon propagates. Okay. Now, if I make the initial state arrow, if I do this, then this is basically representing an electron scattering, because both the particles are particles or rather electrons here. Well, it is not necessary that when we talk about QED, we have to talk only about electrons. We can talk about any charged particle, so to say. So, basically you can say, okay, I can have muons, I can have tau, you remember all your charged leptons. I can have quarks, right? I can have a up type quark getting scattered. I can have a down type quark. So, I have all the possibilities, but remember that I do not have the permission of mix and matching. I cannot have a electron and going to a muon. No. I can only have an electron, because remember the interaction terms allows you to have only one kind of psi in it, psi bar gamma mu psi mu, right. So, if psi represents electron, then the psi bar will be actually outgoing electron, or the next possibility is which I am coming to. So, electron scattering or muon scattering or tau scattering is one possibility which is represented by this vertex. Similarly, I can actually reproduce electron positron annihilation. That means, electron and positron both are coming towards the vertex and getting annihilated. So, how do I draw the momentum graph? So, if this is electron, then the momentum is actually flowing towards the vertex, and this fermion line is flowing out of the vertex, but the momentum is flowing towards the vertex. So, therefore, this represents a positron, right. So, this is a positron electron annihilation, and once again you can say that I can very well have a tau plus tau minus annihilation, mu plus mu minus annihilation, where exactly I draw the momentum and the vertex arrow in this particular way. And this is of course the wavy line represents the photon. Okay. I can have a positron scattering. How? I draw the arrow once again in the similar direction, but now you see that how I draw this momentum to flow towards the vertex and this one to flow on this direction. So, in both of the cases you see the momentum arrow and the fermion arrow are opposite. So, this is actually a positron scattering, right. So, the positron is coming to the vertex and positron is going out, and similarly you can represent this by a muon scattering or a tau scattering, and of course, a quark scattering. You are not limited, right. So, any possibilities is embedded by this so called QED. So, this is the positron scattering. Well, you can say that I can also have represented it by mu plus scattering, tau plus scattering, and so on. And similarly, I can have one last possibility, which is to produce a pair of fermion and antifermion, like electron positron production. So, I am once again keeping the fermion arrow in the same way that I actually had. Now, I have to choose the momentum arrow appropriately. Dekho, I want this to be electron positron creation. So, I draw the momentum arrow for this one. this is actually going out of the vertex. So, it is an electron creation. Once again, if I choose the momentum arrow in this direction, so this is actually having a opposite fermion flow to that momentum. So, this is a positron. So, this is a positron creation because the momentum is coming out of the vertex, and electron creation which is also coming out of the vertex. So, this is actually giving you electron positron production. So, I think with this we are going to end today's lecture, and we are going to construct some interesting graphs and its amplitude with this Feynman rules that we actually prescribed. Okay? So, thank you very much.